All right, good morning, everyone. Hope you had a good weekend. The top hat code for today is 5550. Today, we are going to talk about parallel algorithms. And my motivation for this particular topic at this particular time is twofold. All right, number one is parallel algorithms is a cool topic. Number two is that it allows us to revisit and to review various topics that we have previously done in this course. And that's good, especially as we are getting closer to our final exam. So you'll see, we're going to see many of the algorithms that we've done before, and we're going to look at them with fresh eyes. All right. So before we get to sort of some nice examples of parallel computation, we need a few terms, right? One term is serial processing. Serial processing means you do one thing at a time, right, in order. Parallel processing means that we can run multiple processes at the same time, all right? Where do we run them? So we need to have different processors, right? So sometimes we can simulate multiple processors by allowing our one processor to alternate between different tasks. But that just creates a lot of overhead. So what it does is it eliminates what they call starvation, which is one process waiting for a long time for its turn, because this way it'll get its share of the computation time. But for our purposes, we're going to be assuming today that we have separate processors that can run the different processes. Okay, so in a course like operating systems, you learn about how that happens behind the scenes, right? We also have something called multi-threaded, which means they're being run as separate threads, but we don't necessarily know just because something is multi-threaded that it's actually running in parallel, right? So we're assuming that we're dealing with something that is actual parallel processing. Now, once you can do things at the same time, this raises some questions, which is what is the relationship between the different processes, right? Particularly if they are sharing some memory. So there are different ways to model this. One way to model this is what we call exclusive read, exclusive write. What that means is that only one process can access the shared memory at any given time. So only one process can read from the memory, and only one process can write to the memory. Okay, why would you do that? It sounds pretty restrictive. Can someone tell me, either out loud or in the chat, whatever you prefer, why anyone would choose this model over some of the other models that sound a little bit more flexible? So I would say two things. Number one, to enable concurrent read or concurrent write is probably more complicated, right? Because you have to worry about them stepping on each other's toes. Number two, they're more dangerous, right? So aside from actually supporting it, there is a risk that one thing is modifying data while the other one is in the middle of doing something with it. So there's some issues there, right? So by saying that only one process is able to access that memory at any given time, that does simplify things, but it also limits us, right? Because it says everything has to wait. So you sort of lose out on some of the benefit of the parallel computation if you can't really have different things using the shared space at the same time. So once we say that, you can talk about having concurrent write, that two things can write at the same time, but they can only read one at a time. They can read at the same time, but they can't write at the same time, or they can read and write at the same time with whatever those issues that entails. All right, so we are going to use three commands we're going to introduce. These are pseudo commands, but any language that supports parallel computation would have some equivalent to these. So they might not call it exactly those three words, but they would have some way of doing something like this. All right. don't worry about this. These are some different models that we have. This is not important. Well, okay, maybe we'll talk about it a little bit. All right, so what does a data parallel model mean? Data parallel model means that you have different data streams, and each data stream feeds a different process on a different processor, right? A task graph model means you have multiple tasks going on. We could have a work pool model where you have different processes that are all accessing this work area. You have a master slave, although we don't call it that today, right? And then we have a pipeline, all right? So again, that's just a little bit of background information. What we're going to do now is to really help you appreciate these concepts is we're going to try a few examples, okay? And again, all three of these examples are examples we've seen before when we are dealing with a serial processing model, right? So before we do that, we need some special terminology and notation for working with parallel algorithms, right? So in the past, we often spoke about T of n, right? Many times in our class, we spoke about T of n. Can someone tell me in the chat or out loud, what does T of n stand for?
Recurrence function?
Okay, it's a recurrence relation that represents what? So it's a recurrence relation that represents what? Time complexity, right? It's the number of operations that is required for whatever algorithm or whatever problem, right? For n input size n. All right, so now things get a little bit more complicated, okay? Because we don't just talk about T of n anymore, we talk about T sub 1n. This means the time or the time complexity, right? When there is only one processor. Because now we're in parallel world, right? Where we could have more than one processor. So we can also talk about T sub p n, which means what is the time complexity when I have p processors? And then we can go one step further and say, what happens if I have infinity processors? Now, in reality, you can never have infinity number processors, okay? Because it would take infinite amount of time and infinite amount of resources to create infinite number of processors. So what we really mean is you can have as many processors as you need, right? So remember, our input is also not infinite. So we don't never really need infinite processors, even if we could have them. So it really means as many processors as you want. Okay, and now we come to a very important measure, which is the speed up, which is if I take the time, the number of operations it would take if I only had one processor, and I take the time, the number of operations it would take if I had as many processors as I want, what is that ratio? And we call that ratio the speed up. The bigger the ratio means what? It means that this is much smaller than that. So it means I'm getting a lot of bang for the buck, as we say, right? The processors that I'm using are helping me. Whereas if this number is, let's say, close to 1, that means that even though I'm introducing a lot of processors, it's not really helping my ratio. I'm not getting it much faster than what I had before. So this is a number we're going to be looking at for each of these parallel solutions that we talk about here. All right, so our first example is the recursive approach to calculating the nth Fibonacci number. Okay, if you recall, what was the time complexity of this algorithm as implemented?
Exponential.
It was exponential, okay? So more specifically, it was on the order of 1.6 to the n, right? Where did that come from? Well, if you solve the recurrence for how much work it's being done, you get something like this, 1.1 plus square root of 5 over 2 to the nth power. Actually, there's also a second term, 1 minus square root of 5 over 2 to the nth power, but that number is a fraction. And if you raise a fraction to the nth power, you get something that converges to 0. So this is the term that dominates. This term does not. Okay, So again, this is the, if you were in intro to programming and you learn about recursion, they said, okay, let's do the Fibonacci numbers. This is probably the way you would code it if you're doing it in Python. In Java, you make slight syntactic changes, but basically, I got a little typo here. Might as well fix the typo here. Okay, so we need a little colon there, a little colon there. Okay, so that's the serial version. So without cheating, can anyone see how we might use parallel processing to speed this up, or at least try to speed it up? So does anyone see maybe some sub problems here that we could try to run at the same time?
Memoization.
There is something called memoization, but that's not the question here. I'm saying, do you see something here where we could use parallel computing, right? There are multiple subproblems that could be solved at the same time. So memoization is another technique that has to do with remembering old results. I'm saying, look at the code the way it appears on this slide, and do you see something that would be a good candidate for parallel computing?
Different recursive calls.
That's right, different recursive calls, right? So we have one call to Fibonacci with n-1 and another call to Fibonacci with n-2. So instead of doing one, waiting for the answer, doing the other, waiting for the answer, and then adding them, why don't we try to solve both of them at the same time using different processors, and then we add them together, right? So we would expect that to be a lot faster. All right, so that's what this is doing. Okay, so this is saying create a parallel version of Fibonacci, right? We have our base cases as usual, so that hasn't changed. But the recursive part, look how it's done. We solve the subproblem on the left. We spawn a separate process for the right, and then we sync. Okay, what does sync mean? So if you're programming Java, probably familiar with that term. Synchronize, what does that mean? It means basically wait for them to hook up with each other, right? So it's saying, okay, don't do anything until these are done. Wait for them to catch up, right? Once we catch up, we have a value for X, we have a value for Y, and we can add them together. We obviously don't want to add X to Y if X hasn't finished yet or Y hasn't finished yet. So this says do this in parallel, wait for them both to be done, and then add them up, right?
When
So
you
fairly straightforward. What?
When you say wait for them, do you mean like wait for the variables to get their value?
Correct. So whatever it is that, the operating system says, okay, this subroutine has been completed, right? So it's saying wait for that, wait for it to be done. All right, so we're going to analyze this. All right, so let's do this. Okay, we're going to compute this fib n-1, and let's assume that that takes t of n-1 time, because that's appropriate, right? And this one's going to take t of n-2. All right, now keep in mind, this is parallel computing now, right? So these are happening at the same time. So here's our new recurrence. Everyone see this new recurrence? We're saying take the max. This is one subproblem. This is the other subproblem, but they're now happening at the same time. So take whichever one of these is larger and add one. Why are we adding one here? What's this plus one for? So we need to
one more operation here.
We need to add these two results, right? So the plus one says, I need one more operation to add the results of the two subproblems. Now, which of these is bigger? T of n-1 or T of n-2? I need to max them. Which of them is bigger?
n-1.
T of n-1 is bigger. Okay, so here's my recurrence. right? If I'm taking the max of these, the max is t of n minus 1. Where have we seen this recurrence before? Bunch of places, but I think the first one was linear search, right? Because what am I doing? It's like decrease and conquer, right? I have one operation to check the current position, and then I have n minus 1 things to go. So this is a very simple recurrence. It's like the most basic recurrence you could possibly have, and its solution is just n. So look at this, all right? Look at this. We're saying when I have only one processor and I implement it recursively, then what's my time complexity? 1.6 to the n. If I have arbitrarily many processors, and this becomes my recurrence, what was my time complexity? N. So my speed up is 1.6 to the n over n, which is exponential speed up. That is very good. Okay, now the question is, why is it so good? Why did it end up being so good? Is it because we did something brilliant here? What's the real reason that we got such a good speed up here? So the reason we got such a good speed up is not because this is such a brilliant insight. It's because our original algorithm was so bad. All right. This way of computing Fibonacci numbers, as we already know, is just really bad. Now, the truth is, this speed up is also bad. You know why it's bad? The n isn't bad. The n is as good as it gets. But the number of processors that you're actually going to use here is really exponential. And just like we can't afford exponential time, even more true is we can't afford exponential processors, right? Certainly not in a regular model of computation. Okay, so this is good for illustration purposes. In practice, it's really not so useful because we could get linear time for Fibonacci with using plain old iterative approach. And number two, using an exponential number of processors is not really so practical, but it is a good illustrative example. Okay, any questions about this example? So this one's fairly simple, I would say. Next one's going to be a little bit more complicated. Merge sort is going to be a little trickier than that. Anyone have any questions? All right, so let's move on to what we call matrix vector product, MVP. So in baseball, MVP stands for the most valuable player, but that's not what we're talking about. We're talking about the matrix vector product. So the matrix vector product, we take a matrix, this, we take a vector, which is just one column of a matrix, and we multiply them. How do we multiply them? Well, we take this column here and we do a dot product with this row here. Take this column here, you do a dot product with this row there. All right. Can anyone suggest how long this is going to take before we get into any parallelization? So just, if you were coding this in Python or Java, and someone gave you an n by n matrix and an n by 1 matrix, what would be the time complexity?
Polynomial.
Okay, I agree with you. It would be polynomial. Can we be more specific, though? So I'll give you a hint. What is the plain old matrix multiplication, right? So you did an assignment on that.
N square.
No.
N cube.
N cubed. Now, that was for an n by n matrix, okay? If our second matrix is only one column, what do you think it would be able to do? N squared. Let me tell you why, right? Think about what we're doing here. We're multiplying this by this, the 5 by the 0, the 1 by the 2, and the 8 by the 0. That was n operations, right? Then we do the 2 by the 0, and the 5 by the 3, and the 1 by the 0, and the 8 by the 4. That would be n operations, right? So each row times the column would be n operations, and we have n rows, so that's n squared. So to do a matrix, n by n matrix by an n by n matrix is n cubed. To do an n by n matrix by an n by 1 matrix or a single column is n squared, all right? So that's what this is, okay? This is the code to do it. This is Python. Okay, very simple code, right? And this is going to be n squared. It's easy to see that it's n squared because you have a nested loop inside another nested loop. Each of them are just a simple, n size. So it doesn't get much easier in terms of calculating a time complexity. Okay, any questions about the serial version of the matrix vector product? All right, so we're going to move on to our parallel version number 1. So in our parallel version number 1, we are doing each row separately. Okay, so let's go back to this for a second, right? We're saying, let's take this 2518, do a dot product with this row, and at the same time, meaning on a different processor, but at the same time, we're going to take this column here and do a dot product with this row. And at the same time, we're going to take this column vector here and multiply it by this row, right? So that's what this is saying here. It's saying for each row of the matrix, in parallel, we're going to do a dot product. Right, we're going to do each row at the same time. So what's the time complexity now? If each row takes n, but I can do all the rows at the same time, so what's my time complexity?
N.
N, correct. All right, so here's our analysis. Okay, so let's take our analysis. All right, so each one is O of n time, right? If I did it with only one processor, it was n squared. So I have n squared divided by O of n is O of n. So I committed as many processors as we had. And what was my speed up O of n? It's linear, all right? So we're not so happy with that. Now, let's go back to this code for a second. And is there anything else here that looks like maybe we can make that parallel as well? So we made the outer loop parallel. Is there anything else that looks like, well, why don't we try that?
The inner for loop.
The inner for loop, what a good suggestion, right? Why don't we do each, order pair, right? So, the element from one with the element from the other and multiply them at the same time, right? Basically, it means putting a parallel statement around the inner loop. Anyone see why not? And I'll give you a hint. The problem is not this star, it's this plus equals. Okay, let's back up for a second. And let's go think about a bank for a second, okay? So let's say you make a deposit in the bank. Okay, so we have a question from Daniel here. What does Daniel say? Daniel says, so a computer wouldn't do multiple tests in parallel by default. We have to write it in the code for it to do that. So there are situations where the compiler says, okay, let me do that in parallel. So all you have to do is sort of press a button that says, do whatever parallel you can, and you rely on the compiler to figure out whether it should be parallel or not. So, okay, I was just responding to Daniel there. There are situations, so either it can make mistakes, or it may not do it the way you would really want to, or it may create parallelization where there is a risk. Okay, so Ming says race condition. What is a race condition? So let me go back to my bank example for a second. So what happens when you go to the bank? Okay, so I have 40 nickels here after my next class, I'm going to go to the bank and deposit my nickels. Okay, so what happens? And so this is worth $2. Okay, so what happens? They ask you at the bank, right? They ask you at the bank, would you like your balance? So what do? They take what your balance was, they add whatever you deposited, so $2, and they increment it by 2, right? And that's your balance. Now, what happens if your spouse or significant other was also making a deposit at the same time? So they're going to look at what that balance is, and they're going to add that number. But there's a possibility that what you're reading and what you're putting back into the balance are being updated at the same time. Remember what we started with over here, right? So back on that slide, one of the early slides today, we had concurrent read, concurrent write. There is a possibility that they are trying to access the same thing. So when we say plus equals, what happens if the two processes are both trying to add to what's there at the same time? They're going to take the old value, add their value, and put that back in the bucket, in the slot, but one of them is going to overwrite what the other one was doing. So that's what Ming-Lei correctly called a race condition. And some very bad things have happened because of race conditions, where multiple processes are trying to access the same data, and they land up stepping on each other's toes. And by the way, they're very difficult to debug, because when I run it, I may get a race condition. When someone else runs it, they may not get the race condition. It depends on just how things work out, what's happening at the same time. So they are very difficult to debug. So that's the problem with this code on the surface. The problem with this code on the surface is that we are trying to take whatever sum we have and increment it by some value. And we're afraid that one of them is going to step on the toes, okay, as opposed to the outer loop. Each row, go back here for a second, each row of this is completely independent of the other rows. So there's no risk of them stepping on each other's toes. All right, but watch this. Okay, we are going to do a trick here. We say, how many results are being computed in any given row? N. So you know what we're going to do? We're going to say, let's break up that problem. Okay, so I don't know if you can see it. I don't know, my chat box might be in the way. I'm going to move the chat box out of the way. We say, listen, we're going to break it up. And we're going to say, compute each thing separately, and then add. Add the first two terms, add the second two terms, add the third two terms, and so on and so forth. Okay, is that a race condition now? Is that a racing condition? If I say one process is going to add the first two terms, the second process will add the next two terms, the third one will add the third two terms. Is that a racing condition?
No,
No, why not?
because they have their own values.
They're all independent of each other, right? The first two terms and the second two terms have nothing to do with each other. The third two terms have nothing to do with any of those, right? Then we take the first two terms of that and we add those. And we take the third and fourth two terms and we add those. And the fifth and sixth and add those. Once again, they are not stepping on each other's toes because they are independent of each other. And we repeat that process. Does this remind you of anything, by the way? It's a little bit similar to something else we did in this course. It's a little bit like merge sort, right? Because you're taking the two small things and combining them, two small things and combining them. It's that merge sort, everything we did was, one at a time. But it's sort of like merging, right? We're merging the D1 and the D2. We're merging the D3 and the D4. We're merging the D5 and the D6, but the merge in this case is actually addition. Then once we do that, we merge the E1 and the E2. But what was the E1? The E1 was this sum. The E2 was this sum, and so on. So now how long is it going to take? How long will it take to add these all up?
Linear time?
Well, it's actually better than linear time. So first, let's do this one row at a time. So these two rows here, these two lines of code, how long does it take if this is being done in parallel? Constant time, right? Because each pair, this is an element and this is an element, is being done at the same time, right? This is in parallel. So this little loop here is constant time, one operation. Then this is going to do n over 2 operations at one time. So that's one operation. The next row is going to take n over 4, but all at the same time. So how many times can you divide n by 2 before you get down to 1? So that you should know, right? If I take n and I divide it by 2, and I divide it by 2 again, and I divide it by 2 again, how many times can I do that before I get down to 1?
N times?
No. If I divide it by 2 and I divide it by 2 again, I can't do that n times.
Log in.
Log n, log base 2 of n, correct. All right. So let's review what we have here. Okay, we have an outer loop, but the outer loop is happening all at one time. So it really boils down to the inner code, right? In the inner code, we have this thing, but this is happening all at one time, right? Each pair of elements is being done simultaneously. This is just order 1. And then we have these parallel statements, etc., right? They're log n. Each statement is one operation, but they're log n of these statements. So look at our new time complexity, all right? We have O of 1 time for multiplications, all n squared done in parallel, but we have to do our additions, right? And we have to do it in this careful way so that we don't step on each other's toes, and it's log of n time. So our total time is log of n. Why log of n? Let's just go back to the code here for a second, right? Because we have log n of these statements, right? We're adding them in pairs, then the pairs get added to each other, then those pairs get added to each other, and so on and so forth, right? So this is just showing you the parallel addition, what is actually being computed, right? So the total time is log of n. So what is our speed up? Well, to do the MVP with one processor was n squared, right? That's what you saw over here. That was n squared. And then this one here was log of n. So our speed up is n squared over log of n, which is close to quadratic. Okay, it's not quite quadratic because we don't have O of 1 on the bottom. The log of n grows very slowly. So this is near quadratic. Okay, so that's good. Okay, so this parallelization wasn't so good. It was only linear. This parallelization is is close to quadratic. It's close to n squared, right? So often we have to think creatively when we do parallelization. On the one hand, we have to be careful about things like racing conditions, what we can actually parallelize. On the other hand, sometimes if we're creative, we can do things more. So back to Daniel's question from earlier, right? The computer isn't always so good with creativity. Sometimes it is, and sometimes it isn't. So we might have to guide it along and say, you know what, this is what you need to do. So that's why we have computer scientists studying parallel algorithms. All right. There's a concurrency control, but concurrency control is a double-edged sword. So concurrency control prevents you from doing things that are at risk from each other, assuming the concurrency control is working properly, but it also may restrict you, right? It may say, okay, so we're not going to attempt that because it looks like the way this code is written, it looks like we need to wait for the other thing to finish. Okay, so you're not really getting the benefit of the parallelization. So that's the drawback, right? The computer doesn't figure out how to do this in a way that is, you know, as smart as we can. Okay, so this is one of my favorite examples of the course, really, is a merge sort, okay? But it's not the merge sort that interests me, it's this parallel version of the merge sort. Okay, so remember how merge sort works, right? Merge sort takes an array from position low to position high. It finds the midpoint of those. It merge sorts the left half, it merge sorts the right half, and then it merges those two together. And here's a recurrence equation that we've seen many times in the course. There are even some messages about it on Slack over the weekend, right? And remember this recurrence equation. What is A in this situation?
2.
2. And what is B? The number of subproblems?
2.
The relative sizes. I'm sorry, A is the number of subproblems. B is the fraction of one subproblem compared to the original. It's a half, so it's 2. And C is the degree of the polynomial in the other part, the combine and divide part. So that is 1. Right? So we use the master theorem, and we conclude that it's n log n, or we could derive a closed form formula. Okay, so we're not going to derive a closed form formula today. That we've done before, and we have slides and stuff for that. All right, question is, can we do better than this? Anyone have any suggestions? So there are two suggestions, okay? One suggestion is obvious, one suggestion is less than obvious. What's the obvious suggestion here? Where could we use parallelization? What do you say?
We can use that in recursive calls.
So be more specific. I think you're on the right track there.
Like on the
Forward
second
call.
recursive call.
Okay, so we have a call to merge sort on the left side of the array. We have a call to merge sort on the right side of the array. The way the code is written right now, it's going to do one, and then it's going to do the other, right? In a parallelized version, we could say, do them at the same time. Use one processor to work on the left, one processor to work on the right. And of course, they're going to do recursively, so they're going to use more processors. That's the basic idea, right? So we could, okay, so we could basically spawn a separate process for the right-hand side. And then, of course, we have to synchronize, wait for both sides to be done, and then we merge them. All right, can anyone tell me why the merge part is not so easy to parallelize? So the merge, you need all the elements there. Remember, you can't just chop them in half and do like the first half of both and the second half of both. You know why? Because some of the smaller elements, maybe all the smaller elements are in one list. So the way they get integrated with each other, they get merged with each other, they might be, taking elements from anywhere in the list. So we can't just, when we merge them at the end, you can't just say, okay, this process is going to take the first 50% of the elements from here and first 50% of the elements and merge them, because some of those elements in one of the lists may be very large and they need to get merged with the latter half. All right. So we'll come back to that thought in a moment. Okay, but let's take our parallel version number one. We're going to analyze it. So each half takes T of n divided by 2. So that's sort of obvious. But here's the cool part, right? Instead of having two subproblems, how many subproblems do we have now?
One subproblem.
One subproblem. Now we really do have two subproblems, but the reason we write one there or don't write anything is because the two subproblems are being solved simultaneously, right? So from the perspective of how much time is going by, right, they're happening at the same time. Okay, so anyone know how to solve this recurrence? Well, we can use the master theorem. What is A in this case?
One,
And what is B?
2,
What is C?
or 1/2.
No, what is C? C is the power, right? So the power is 1.
Oh, 1. I had the wrong.
Okay, so what's our rule? We take log B of A. So log 2 of 1 is what? Log base 2 of 1 is 0, right? So 0 is going to be less than the 1, the C, and therefore our time complexity using the master theorem is going to be O of n, right? It's going to be O of, it's not the log one, it's going to be O to the of n to the C. Okay, and the C is 1. All right, so is this good or bad? Well, let's figure that out. So the time complexity for merge sort with only one processor available is n log n. Time complexity with as many processors as we need is this O of n. So n log n divided by O of n is log of n. Is that a good speed up? I cut off. Okay, we're gonna try that again.
It was
Right.
when you like what A, B, and C were. You cut off in the middle of that.
All right, so again, A was A was 1. Okay, so in our new recurrence, A is 1, B is 2, C is 1, right? Log B A is equal to log base 2 of 1, which is equal to 0. Okay, C equals 1 is greater than that 0. Therefore, our complexity is O of n to the C, which is equal to O of n to the 1, or simply O of 1. I'm sorry, no, that's a mistake. That's a mistake. That should be O of n. Okay, so that's this O of n. So we take the speed up. The speed up is the time for one processor divided by the time for as many processors as we want. And that's n log n divided by O of n, which is log of n. Is that good or bad as a speed up?
I think fairly bad.
That's really bad. Okay, so just to put things in perspective, the speed up we got for Fibonacci was exponential. The speed up we got for one version of MVP was linear. Then we improved that and we got it to near quadratic, right? N squared over log n, which is near quadratic. Now our speed up is log of n. That is really bad. Okay, why is it so bad? Well, let's think about what we were able to do before and what we were not able to do before, right? We were able to speed up the parallel merges, but not a parallel merge sort. So if you have to wait for everything to, finish before you can merge, and keep in mind, it's not just at the end that this happens, but every recursive call has to synchronize for its respective merge. So that is not good. Okay, so this approach is not good. Why do we do it though? Well, first of all, I can teach you how to analyze it. But number two, and we've seen this so many times in the course, sometimes to get the good improvement, you have to go through a bad improvement. I know that's an oxymoron, but it's like an improved way of thinking, but not quite yet. So we've seen that with long integer multiplication. We saw that with matrix multiplication. We saw that with closest point problem. Many times we started with an idea, looked promising. It wasn't so promising, but then when we tweaked that idea, we found that it actually could be good. So the question is, can we do a parallel merge? And the answer is yes, but we need to be careful about it. Okay, and the trick to the parallel merge is to create two subproblems that are non-overlapping. So just like when we did the matrix multiplication, right? Created the two subproblems that are non-overlapping, right? You have, separate rows, and then within the separate rows, you have separate pairs that are non-overlapping. That's the key to parallelization. If you can break it up so that they're non-overlapping, then you can do it. Now, sometimes they will be overlapping, but then you just have to be much more careful about what you're doing so that it doesn't create a problem. So here's the trick, all right? I'm going to summarize it, then we're going to look at it in some detail. Okay, so the trick works as follows. You take the midpoint of one of the two arrays, and I'll tell you in a moment which one, but for now, it doesn't really matter, right? So you take the midpoint, okay? The midpoint we're going to say is 40. Okay, that's the midpoint. All right, now what we do is we then look at the second array. Now keep in mind, these are both sorted. This is after the merge sort has done its part. And we say, find the point in the other array that has, such that everything less than it is, everything to the left is less than 40, and everything to the right is greater than 40. Okay, why are we doing that? Then I'll get back to the how, because now we have all things 40 or less over here, all things 40 or less over here. We can do a parallel merge. And we can do a merge on the light blue, and we can do a merge on the purple. Is that how it's coming across? You see blue and purple, or lavender or something like that, right? So again, once we break up our two arrays such that, everything on the left side is less than some number and everything on the right side is greater than some number, we can do a parallel merge. Now, how long does it take to find this midpoint here? So if you have a sorted array, or even if it's not sorted, but certainly if it's sorted, how long does it take to find the midpoint?
Log n.
Nope. I'll give you a hint, binary search. So I'm not asking you to do a binary search. I'm asking you to find the midpoint or merge sort for that matter. How long does it take to find the middle of a list?
Constant time if it's, I mean, sorted.
Constant time, right? So since it's sorted, we can find the median, right, halfway in constant time. Okay, good. Now the other part is a little trickier. How do I find where in the other array that 40 would go? So now, Ellie, I'll take your suggestion.
Log n.
Log n. Why log n? Because I can use a binary search to find it. Okay, maybe I can even do better than binary search, because when we talk about search algorithms, we learned that there are some other algorithms out there that might even be better than binary search. Okay. So now I promised you I would tell you, so how do you decide, right? We're using different algorithms for the two sublists, right? One of them we're just using the midpoint, and the other I'm using binary search. How do I decide which is which? So the truth is, the way it's displayed in this screen, it doesn't really matter, because they're both of the same size. So one of them is going to be order 1, and one of them is going to be log of n. But as you run this, okay, this parallel merge is not going to have equal sizes, because as you can see, when I merge now, I have 6 elements here and only 2 here, so it's not going to be equal sizes. So the rule of thumb is you find the median in the larger of the two arrays, because that's constant time. And then you do the log of n search, the binary search, on the smaller of the two arrays, because you want the log of n is a bigger time complexity, so do that on the smaller array, right? So once we do that, now I can do a parallel merge. I do a merge on all the light blues from the two lists, and I do a separate merge in parallel on all the purples, on the lavender color, right, in a different merge. And of course, this is well, actually, it's not done recursively. All right, so that's our parallel merge. Now we're going to analyze it again with this in mind. Okay, so here we call this parallel version 2. All right, parallel version 2. All right, so we have, sorry, it's just finishing to convert my previous class. I just need to save it, and then we'll be back to you. All right, so watch this, right? I have 2 subarrays, okay? In the first list, it's guaranteed that it's going to be split 50-50, right? So that's this n over 2. Okay, well, let me take that back. Each list is n over 2. Half of one of those is n over 4. So that's where this n over 4 is coming from, saying I'm guaranteed to have only n over 4, right? In the other one, I might not get so lucky, right? I might get all the elements on one side and no elements on the other side. So that's where this n over 2 is coming from, right? Now, Ellie, where did this log of n come from? I'm asking you for a reason.
That's how long it took to put each one on the side of the.
That's the one that determined where the pivot point, if you want to call it that, in the second array was, that matched, more or less matched the median of the other one, right? So that's the binary search. Okay, so we have this recurrence. Okay, this is not a recurrence I'm going to ask you on the exam, right? At least not to solve it, right? Is this, right? It's saying, okay, the time is 3/4 n plus log of n. And the solution to that is log n, log n, log n, okay? Log n times log n times log n, right? Not log n. Log n times log n times log n. Okay, that is not obvious. Okay, I would not expect you to solve that, but just take that take that for granted. Okay. So what is our speed up now? So once again, the same methodology applies, right? You take the time for one processor, divide it by the time for arbitrarily many processors. So we know the time for one processor is a merge sort is unlike n. The time for arbitrarily many using this new approach is log cubed of n. So one of the log n's cancels. So we get n over log n times log n, which is close to n. Okay, it's not quite n, but it's close to n. Okay, this is considerably better than version 1. Okay, version 1, the speed up was log of n. Here we're getting closer to n. Okay, it's not as dramatic as, let's say, what we got for Fibonacci, but it's good. Keep in mind that the reason the speed up isn't so good, it's not because we didn't come up with good ideas. We came up with good ideas. The merge sort already is a pretty good algorithm. So the better the algorithm to start with, the less good the speed up is going to be. Okay. I just want to see something here. Okay. All right, so it's not on the slides, but before we go any further, so here's a question for you, right? What about parallelization of quicksort? Any thoughts about that? Okay, so let's write some pseudocode for quicksort here, right? So we have quicksort of your array A, you have a low, and you have a high. So what do we do inside there, right? We find our pivots, right? We partition A, low to high. Sorry, we need to get a pivot, right? So how do we get a pivot?
We choose one randomly.
Okay, we could pick one random. So we could say, I don't know, random. I'm not using proper, so let's say random. Between low and high. That's going to be our, and then we partition it, right? So you partition it A, low, high, and the pivot. And then we do a quicksort recursively on A from low to pivot -1. And we do a quicksort on A from pivot +1 to high. Okay, so that's the basic idea of quicksort. So does anyone see any opportunities there for parallelization?
Yeah, we could do the low to high minus or pi -1, and then
Okay, so the two calls to quicksort, instead of running them in serially, sequentially, we could run them at the same time. All right, anything else? What about partition? That's the other choice, right? So finding the random integer, that's straightforward. What about the partition parts?
I mean, I would think you could do it. You could just have one like task checker, like the first half the elements, the second one took the second half or something like that.
So we could break it up, right? We could break up the data, okay, and say, all right, you're each getting, some of the data. Maybe one gets one side, one gets the other, and you break it up into two parts, all right? So that per se isn't so crazy, All right, you will have a little bit of a space management issue because one of the things we do in partition, we don't just figure out if things are small or lower, but we also put them on the right side. So now if you've got, two different sources of information, you might need to create separate lists. So that will be worthwhile, I would say, if you have a very large list, okay, to get that parallelization going. If you have a small list, so the overhead of creating these separate lists so that you can do them simultaneously, that might be more expensive. Sort of like what happened with a counting sort. The counting sort looks good on paper, but some of the allocation of space turns out to be very expensive, especially when the lists aren't so worthwhile. All right. So there are certainly some possibilities here, but partition would be a little bit careful. Okay, so just to take these theoretical concepts and talk about how you might do this in a language like Python, right? So first of all, you need the right package, all right? So as you already know, even if you never saw Python before this course, is the trick to Python, the trick to a lot of languages actually, is making sure you import the right package. Okay, when you have the right package, so jobs become a lot easier, right? So in this case, the package, the magical package is something called multiprocessing. You give it an alias, we call it MP, and then we can use a CPU count, all right? So in the analysis we've been doing until now, we've been taking for granted that we have infinitely many processors, which I told you is not true, but what we're really doing is assume we have as many as we want. That's also not true. Okay, how many processors are you likely to have? If you're on a desktop or a laptop.
4.
Something like that order of magnitude, right? Okay, so you don't really have as many processors as you want, right? Okay, so these are some of the commands that we have, right? We have a synchronous approach, which means we want to wait for something else to happen, and an asynchronous approach. All right, so here is some basically simple problems, right? So again, we're going to look at it from a serial approach and then from a parallel approach, right? So we have a row, which is just a list, and we want to find out how many numbers are within a certain range. Okay. Why would you want to do that? I don't know. So let's say we're looking at test scores. You're saying anyone who is in that range has to take the exam. Okay, if they're outside the range, if they're doing so well in the course, maybe they don't have to take the exam. And if they're doing so poorly, well, the exam isn't going to help them. So they're going to fail anyway, right? So whatever the reason is, okay, we want to get the number that are in this particular range. So how do you do that? Well, you iterate through the items, right? So that's what this is doing here. We iterate through the items and we check, and Python lets you do this in one line, right? You check wherever n is between the min and the max, whatever boundaries you want. And if it does, then you increase the count and you return the count. Okay, and then you can call that function. Okay, so actually what this is doing is it's running this for a whole bunch of rows. See that? Right, so this function here is for one row, but this code here is for a whole bunch of rows. So it's saying, okay, for each row, tell us how many are between 4 and 8, right? So what is the time complexity of this function by itself? O of what? So this first function here, ignoring the fact that it's being run a bunch of times.
Whole thing.
Not n. N is just, in this case, n is just a variable, right? A loop variable. It's O of the length of row. So we don't know how big row is, but however big row is, that is the time complexity of this algorithm. Now that in turn is being multiplied by, what's the time complexity of this? The O of the data, right? So the time complexity here is O of the size of data times the size of row. Okay, that's the time complexity, which we would call an n squared algorithm, but n is really meaningless because we're not defining what n is. N is something else in this problem, actually. Okay, so does anyone see some opportunities for us to parallelize this?
Yeah, I mean, we can do each row separately, right?
We could do each row separately from the other, correct? What about within each row? So doing each element of the row separately.
Is it the same, like, kind of like we said last time, we can split the elements up into separate parts?
All right, so it's not that simple, right? That's that's the first answer. It's not that simple. Why is it not that simple? Because we have a racing condition, right? You are adding to some, count that is being, continually updated. So there is a risk that when you take whatever is in the bucket and you add one to it and you put it back into the bucket, that something else is accessing the bucket in the middle or changing the bucket in the middle. So there is that danger. So you could do this by breaking it up in that binary kind of fashion, but that is something to watch out for. All right. So here is our time complexity. So you take the number of rows, take the number of columns. So again, the number of columns here, we should actually write this in the slide. The number of columns here is equal to the size of row. And the number of rows here is equal to the size of the data. Okay, so here is some code for actually doing this. Okay, so we import the multiprocessing. Okay, we create a pool of processors, and we create a pool using all the processors that exist. So this is also a greedy algorithm in a certain sense, right? We're saying, give me all the processors that we have, right? However many, whatever that count is, I want them all. And then we call the pool apply, which is applying our processors. And we say, call this how many within range, which was this first function here. Am I missing some semicolons there? No, the semicolons are there. They're just not showing up. Interesting. Okay. All right. So I call I don't know what happened there. Right. So I call these, I apply my pool of processors to how many within range for each row simultaneously. All right, and you got to watch out for this. So just like when you use databases, you have to close your connection. So it's important to close the pool. Why is that important? Now, it might happen automatically, but why do you think that this might be a good idea?
So your processes aren't just taking up doing nothing?
Yeah, so we want to sort of reclaim those processes so that, if something else wants them, they can have them. All right. And then we're printing the results here. Okay, this is just a Python notation if you're not familiar with that. Right, that's getting everything up to position 10 of the array. Okay, so let's do our analysis again. So as before, we are not doing our columns at the same time. The reason we don't do our columns at the same time, we're concerned with that racing condition, and we haven't necessarily, decided to use that trick where we're doing, pairs, let's say, and adding them, together. It's sort of like a tournament model. I didn't use that word before. It's sort of like a tournament model, right? Because what happens in a tournament, you got n teams, and you do them in pairs. You have n over 2 pairs. And then the winners of those pairs move on to the next round. So you have n over 4 teams, n over 4 winners, and then n over 8 winners, and so on and so forth, right? So that's what we call a tournament model. Okay, so again, we had R times C if we use a completely serial model. If we go with this parallel model, we get down to the number of columns because we parallelize the rows, but we still have work per column. So it comes out to O of R, which is roughly the equivalent of an O of N speed up. Okay. Okay, so what are we doing here? Yeah, so this is just a different syntax. So you don't have to pass in so many stuff. I don't know why we're. Okay, so this is just applying list comprehension to it. Nothing really interesting here from parallelization. Okay, we're going to move on now to another application of this. Okay, prime factorization. And we've seen, have we seen prime factorization before? I'm not sure. We will see it again. We do it in numerical algorithms. We did something to determine if it is a prime, right? But we didn't do prime factorization.
I think we use the opposite of that in one of the encoding algorithms, where you use prime factorization to make like the encoding of a word.
To make,
You could always take the most recent, the next prime, I mean like 2, then 3, then 5, and raise it to the power of whatever the next character in the word was.
yeah, where do we do that?
Wasn't one of the encodings? I don't remember which like lecture it was, but I think it was Gödel's encoding. Maybe I might have the name wrong.
Oh, Gödel? Oh, yeah, that's the other course though. That's 320. Not with me. I mean, I'm glad that you know about that.
I thought we covered it in one of these.
No, we didn't do that. No, and data compression, we also didn't use it. There's something called RSA. RSA is a kind of encryption where I use that, but we didn't do that. And hashing, I mean, yeah, hashing definitely uses prime numbers. Okay, so this is prime factorization. What is prime factorization? Prime factorization is trying to find out the prime factors of a number. Okay, so for example, if I have the number 6, okay, so what is 6 equal to? 6 is equal to 2 times 3, right? Those are the prime factors of 6. Okay. All right, so here's an example. We call lowest factor with 100, and we get a 2. Then we take that 2, and we get the lowest factor of 50. That's 2. Take the lowest factor of 50 is 25. Lowest factor of 25 is 5. And so we take all these numbers, and we get our prime factors that way, right? So here is an example. Okay, so here are some numbers that are not so simple, right? You look at these numbers and you say, huh? What's the prime factorization of that? So this is not something you do on your head. This is where a computer comes in and is helpful. Okay, so what we're doing is we are calling the lowest factor function. Okay, and we're starting with 3. Okay, so we say as follows: if n mod 2 is equal to 0, so what's the lowest factor?
2.
2, right? It's 2 because it's even, right? So n mod 2 equals 0 means that it's even. So then the lowest factor is 2. Now that doesn't mean it's the only factor, right? This function does not find the entire prime factorization. It finds you the lowest factor, right? So we return 2. Otherwise, okay, what we're doing is we are finding, all right, we are finding, okay, so that, I don't know why. It's very weird. You see there's an underscore there? Everyone see that? There's an underscore there, and when I make it big, looks like it's not there. Do you see it on your end? Do you see an underscore between the search and the max?
I don't.
You don't, but it's there. That's the weird part. I don't know if it's a font color. See, when you make it big, it looks like it's not there, but here it's there. I don't get it. And it's there if you make it small. It looks Okay, so what we're doing here is we are finding the square root of n, and then we're just rounding that down to an integer. Okay, we're adding 1. So that's the sort of the upper bound of what we need to check. Okay, so again, what we're doing here is we're writing a code to figure out what we need to check. So we need to check, why are we checking in units of 2? So you see we're iterating over the possible factors. Okay, so you start with the smallest factor, smallest possible factor. We don't know that it actually is a factor, right? And we work our way up. Why are we working our way up in units of 2?
It's besides 2, there's no even prime.
Okay, so there are no even primes. So basically we're starting with an odd number, which in this case is 3. And we're saying if 3 doesn't work, let's try 5, let's try 7, let's try 9. Because we know that even numbers have already been, they're already going to be exhausted over here. Okay, so then we check if that number, whatever it is, evenly divides n, then we return that. Okay, so far we haven't done anything here with parallelization. Okay, we imported some packages, but we haven't done any parallelization. Okay, now we have some parallelization going on, right? So okay, this is a little bit complicated. Basically, we're looking over all the different possibilities at the same time, right? So instead of trying one number at a time, we're able to get the lowest factor, and then we put them back together. So that's what the zip is, sort of like a merge function. Okay, and I think that's it. Okay, so we're going to stop there, and I will use the remaining time if anyone has anything they want me to go over. I know recurrences, so I can promise you there will be a recurrence on the exam. So if that's something you'd like me to go over, or any other material. Yes, please. Okay. All right, did we go over the old ones from the last 2 exams? Did we go over those in class? We went over one of them. Okay, so maybe we'll go over the other one. All right, so here's what we're going to do. All right, did I unshare my screen? I think I unshared my screen. No, I did unshare my screen. Okay, can someone tell me, is this the one that we did or this the one that we didn't do? Anyone recognize this? I have more old exams also. Did someone write in the chat? Maybe someone wrote in the chat. We did that one, okay. All right, what about this one here? Did we do this one?
No, we didn't do that one.
We did not do this one?
No.
Okay, so, these are the kinds of recurrences that will be one of the questions on the exam, all right? So, so it's good to be able to understand how to do these things, okay? So the number, the A will change, the B will change, the C may change, although the C usually it's order 1, sometimes it could be order 2. All right, so those are variables. The initial case, the initial condition may change, but the overall strategy is the same, okay? And the sub-questions will also be pretty much the same. So you need to be able to use the master theorem, you need to be able to derive the closed form formula, which is the hard part. And then C is just really a sanity check, okay? It says plug in to the recursive formula, the recurrence relation, and C, if you get the same answer as your closed form formula. Okay, so let's walk through this. So let's do problem A first. So in problem A, you need to look at your recurrence and look at A, B, and C. So A is 125. B is the fraction of, that forms each subproblem. So it's 1/5 of the original. So that's 5. And C is the degree of the polynomial of this extra piece here. And that's 1. All right. So we take log base B of A. So log base 5 of 125. And that is equal to, anyone know what that is? I didn't actually write it here. It's 3, right? Because 5 times 5 is 25, times 5 is 125. So log base 5, 125 is 3. That is greater than 1, greater than our C. So the solution is of the form n to the log base 5, 125, which is n cubed, right? So if when you're doing step B, which is where the hard part, you don't get something that is n cubed, you made a mistake. Okay, so master theorem isn't just a nice, cool thing, but it should be used to as a sanity check against your closed form formula. All right, so we are going to. There's a question on the chat over the weekend, right? When do you do a domain transformation? When do you do a range transformation? So generally, you need a domain transformation when you want to change the domain. The domain in this case is n. And if we switch that to k, where k is, or n is equal to 5 to the k, then n over 5 is going to be easier to deal with, right? So that's a range transformation. So our domain transformation. We're going to assume that n is of the form 5 to the k, which means that k is log base 5 of n, and we use our domain transformation. So that means we're going to rewrite this equation as a function of k, as a function s of k. So we say, okay, instead of 125 Tn of 5, let's say 125 s of k minus 1. Why is it k minus 1? Because if I divide n by 5, that's like dividing 5 to the k by 5. So I get 5 to the k minus 1. Okay, now while we're at it, I say, let's plug in 5 to the k for n. So 5 times 5 to the k is 5 to the k plus 1. Okay, so you're asking, how did we get that n is equal to 5 to the k? It's a fair question. And the answer is, we don't really know that. We don't really know that. We're making an assumption here. And we do that because if we could always round up the size of the input, right? So let's just say the input is really 100, right? The actual size of the input is 100. It's not 100. It's not a power of 5. But we could always round it up and throw in 25 extra elements, right? And we just don't use them, right? So the point is, it's just going to give you like an upper bound, right? So it may not be exact, but the point is, changing it to the next power is not going to change. It's not going to make it wrong. Okay. So that's an assumption that we make to ease this. But really, what you could do is you could say that n is between 5 to the k and 5 to the k minus 1. That has to be true, right? And then you could solve it for 5 to the k minus 1 and 5 to the k, and that'll bound your solution. Okay, so you could sort of say without loss of generality, right? We can make that assumption. Okay, so with that, right? So that our recurrence now becomes s of k equals 125 s of k minus 1 plus 5 to the k plus 1. Okay, and then this is the reason why that's true. All right, but the problem is we still have this ugly 125. See, what we would like to do is get to the point where we can do telescoping. Okay, with that 125 in the front, we can't do telescoping. So what we do instead is we make a range transformation. With the range transformation, that 125 is going to go away. So how do we do that? We do a range transformation, say R of k is equal to S of k divided by 125 to the k. Now, why is that a range transformation? Because we haven't changed the domain. What was the domain before this transformation? What was the domain? K. And what was the domain after? K, right? So we haven't changed the domain. It's still a function of K. What we have changed is a range, because whatever the output of S of K was before, we're now dividing it by 125 to the K. All right. So what I'm doing here is I'm just writing the 125 to the K on the bottom on the outside. I apply it all the way through, and look what happens. This is the beauty of it. This is why I'm doing the range transformation. The 125 here and the 125 there becomes R of K minus 1. Why? Because R of K minus 1 is S of K minus 1 divided by 125 to the K minus 1. So maybe if you like, I could just write that there. Okay. All right. And what happens here? I have 5 to the K plus 1 divided by 125 to the K. Okay. And these sort of cancel, not completely cancel, but I have a 5, and then a 5 to the K over 125 to the K is like a 25 to the K. So that's where this comes from over here. And again, you got to pay attention to your initial conditions. So our initial condition in this case with T of 1 equals 1. So T of 1 is the same as S of 0. So S of 0 is equal to 1. R of 0 is equal to S of 0 divided by 125 to the 0. I should actually fix that. Let's just say here, it's that. Okay, so that's 1 divided by 1 equals 1. Okay, now we get to the good stuff. This is where it starts getting nice. Okay, so I write out all the equations. All right, just keep plugging in K minus 1 wherever you have K. All right, so this K becomes K minus 1. This K becomes K minus 1. This K minus 1 becomes K minus 1 minus 1 was K minus 2, and so on and so forth. So I get this system of equations. And why did I just do that? Why did I write all these individual equations there? I'll write that in the chat. Why am I writing out all these equations? To, take up space, to show how smart I am? Why am I doing that?
Telescope them, cancel out.
Because I want them to cancel each other out. That's right. Because then I'm just going to get the first term and the last term. So look at this. This cancels with this. This cancels with this. This is going to cancel with that. Everything is going to cancel except for this and this on the left-hand side. So we get down to this, RK minus R of 0. Now the right-hand side is a little bit more complicated, right? I have a bunch of terms here. I need to add them all up. And what do we call that? What do you call this sequence of terms here?
A geometric series.
That is a geometric series. Okay, so I have this summation here. I'm going to plug in my R of 0. My R of 0 we determined over here is 1. So I move that 1 to the other side. And then I'm pulling out the 5 from the first term. Is that what I'm doing here? Let's just see what I'm doing. Okay, no, I'm not pulling out a 5. I'm just saying take a minus 5 and a plus 5. I'm allowed to do that, right? I can always add a minus 5 and a plus 5. So I add the minus 5 to the 1 and I get minus 4. And I take that 5 and I make that part of the series here. So everyone see that? Previously, the series was going from J, as J went from 1 to K. Now I'm going from J equals 0 to K. So I'm taking that 5 here and I'm making that part of the series. And now I can use the formula for the geometric series. Okay, so the formula for the geometric series is, okay, we got a question here. Why do we add though? What makes that a valid part of the computation? Okay, so I'm going to answer your second question first. Your second question is what makes it a valid part? And the answer is I can subtract and add any number I want, as long as I'm consistent, right? So I added minus 5 and I added 5, so that's valid. Now you're asking the why. The why is what Ilma said. Oh, you're asking about the telescoping part? Okay, so what's your question there? Be more specific, please, Daniel. I don't understand the question. Okay, I guess you'll ask more if you. All right, so what we do here when we telescope and add, right? So we take all these equations and we cancel that, right? So if you add up all the left-hand sides, all these terms cancel out in this diagonal fashion, except for this one that has no match, and this last one that has no match. So that's how we get this. And on the right-hand side, there's nothing canceling. We just add up all these terms, which is a geometric series as j goes from 1 to k. Did that answer your question? Okay. All right. So now we use our formula for the geometric series. So remember the formula for the geometric series. I'm going to write it here. So write it here. Okay. So remember the formula is A times R to the n plus 1 minus 1 divided by R minus 1. Okay, that's the sum of the geometric series. Okay. Okay, so that's what we're doing over here. So this is our A. Our R is 1/25. We have K terms. And our R on the bottom is also 1/25. So we plug that in, we're flipping these around. All right, where I don't see, Joanne, where you're getting all those 5s from? The fourth line. Which fourth line? In the telescoping and here? Oh, this? Yes? Okay, so we just took a -5 and a +5, right? These two are equal to 0. So I can take any two numbers, -x and +x, and add them. Yes? Okay. All right. So I take this. Okay, what I did on the bottom here is I flipped the sign around. So 1 minus 1/25 is 24/25. And I flip the sign around on the top. So instead of having this -1, I have 1 minus this. Okay, and then what did I do over here? I just pulled this out. So I took the 24/25 in the bottom and I multiplied that by the 5 and I got 125/24. And then I took the 125/24 times 1, and this is equal to minus 96/24. So 125, okay, so here's my -4 is the same as minus 96/24. 125/24 is 125/24. And then I multiply through the 125/24 times this. Okay, so then I subtract these. 125 minus 96 is 29. And over here, I divide one of the 25s through, so I get 5/24 over 1/25 to the k. Just to make you feel a little better, so this exam was given when we were not in a classroom. So everyone had my old exams in front of them. Everyone was allowed to use my old exam. So I had to make it a little bit more interesting, a little bit bigger numbers than what you would get if you don't have the old exams in front of you. All right, so this is probably a little bit more, the idea is the same. The ideas are all the same. So you will have a range transformation, domain transformation, you will have telescoping. The numbers just won't quite be as ugly as this one here. All right. Now we work backwards. So once I have my R of k, I take S of k and multiply that by 125 to the k to get S of k. So I take all that, multiply by 125 to the k. The 125 to the k will cancel out, partially cancel out over here to leave you with 5 to the k. And we get this, and then we plug back in. So what is k? K is equal to log base 5 of n. So I plug that back in. Now here's a rule you need to remember. Okay, if I have something like this, that's equal to n to the log 5 of 125. Okay, so that's an important rule. Okay, so if I have x to the power of log y n, that is equal to, I'm writing this in the chat, that's equal to n to the power of log base x of y. So you definitely want to use that rule. It inevitably is going to show up. So you're using that over here. You're using that again over here. And eventually you get this thing over here. All right. Now they don't cancel out. They partially cancel out, right? So you land up with in response to Cheng, you're going to get 5 to the k. Okay. All right. So the last step when you're testing it is you need to do two things. You need to plug into the original recurrence. So this is the original recurrence, right? You plug in 5. So you get 125 times t of 5 of 5 plus 5 times n is 25. And what is t of 1? Well, t of 1 is 1. We're told that t of 1 is 1. Sometimes it's 0, sometimes it's something else. So I get 125 times 1 plus 25 is 150. And then I have my formula, the formula that we just derived. Okay, so it was an ugly formula, all right? 29 divided by 24 times n to the 3. What is n? N is 5. So I have 29 over 24 times 5 to the 3rd, which is 125, minus 5/24 times n. N is 5, so I get 25 over 24. And I subtract that all out. And I get 3625, right? It's 125 times 29 is 3625. And here I have 25 over 24, I get 3600. 3600 divided by 24 is 150. And
Professor,
yes.
we cannot use calculator on the exam, right?
I don't think so. I don't think so, because once you have calculator, then it becomes a game about what kind of calculator you have. So one person has a calculator, the other person has a database of the course. So the numbers will be simpler. The numbers will be simpler. Things that you can do easily with pen and paper. But I think no calculator.
Okay.
Okay. Okay, so we have a question here. So I like questions. I'm still a bit confused as to why use -5 and 5 in the telescoping. Okay, I'll answer Ryan's question first. So I will land up spending the entire exam checking everyone's calculator. So that's why we're not going to use calculators, because again, I don't know what people have on their calculators. So I don't have the resources to spend an hour looking at 45 students' calculators and making sure that they don't have what they shouldn't have. All right, so back to the other student's question. I guess it was about this. Why did we do this? Why do we put a -5 and a +5? So the answer is, I want to add a 5 into this sum. Because if I add a 5 into this sum, I now have a series going from j equals 0 to k instead of j equals 1 to k, which enables you to use my formula for a geometric series. Now, I'm not allowed to just add a 5 into a series. That's cheating, unless I take what I'm adding into the series and subtract it back out. So if I want to add a 5 to this series over here, I need to compensate for it by subtracting out a -5. Okay, so I'm adding a 5, but I also need to subtract a 5. And then I take that subtracted 5 and I combine it with the 1 to get the -4. But this 5 that I added in became part of this geometric series here. So I can use the formula for a geometric series. Okay, all right. Kidong is saying 5 is equal to 5 over 25 to the 0. I would agree with that. I would agree with that. Why is S of 0 equal to T of 1? Okay, so for that, you need to go back to the very beginning. Okay, so let's go back to the beginning here, right? So again, S of K is equal to T of N, right? That's our domain transformation. So therefore, you say to yourself, okay, well, T of 1 is given, right? When N is 1, what is K? Cheng, when N is 1, what is K? Look at the highlighted there. Okay, K is 0. So that means S of 0 is equal to T of 1. All right, good. All right, so we're basically out of time. All right, so again, these two worked out solutions that you have here in great detail, they were both, remote exams. Okay, so remote exam, I assume that everyone had all my old exams in front of them and they were using it and they were copying and pasting it from it. So I had to make it a little bit more interesting. All right, if you go to some of the other old exams, so we have more of these in there. Okay, some with solutions, some without solutions. So let's see if I can.
I have a question about the exams.
Yeah, just give me 1 second here. I just want to show you what I want to show you here. All right, so this is just some algorithm math. Okay, so here is an example, right? Finding closed form formula, a little bit simpler example. Okay, so this was a in-class exam, more traditional model. So we have recurrence over here. Okay, yes, you had a question for me.
So for the exams, is it good practice to just like, if I'm gonna review for the final, like to just go through the midterm examples? Or should I like go through like everything, like top hat questions and
So
assignments?
the questions on the final will not be little, itsy bitsy top hat questions. So, I would say, look at the old exams. Look at, there are 2 exams that are not in the PDF, and then there are the other ones, right? So let's just go back here for a second. So this is what I'm giving you, right? So these are some old exams. Keep in mind that both of these, from the winter and the summer, last summer, were not remote. So the assumptions about what people had were different. But we have, not necessarily 10 full years of exams, but you have a lot of exams here. All right, these were in-class exams. So the other thing to keep in mind is we have 1 exam in this course, which means it will have, things sort of distributed around. There will be 1 question on this exam, which you're not going to find in any of the old exams. And that is, we spent a lot of time in this class giving you an infrastructure to empirical performance. So I am expecting that after several rounds of this, that you have some idea about how to set up a program for empirical performance. So that is 1 question on this exam, which if you've been doing the assignments, properly, understand what you're doing, then you will be in a position to do that. It's actually an easy question because you don't really have to think per se, you just have to do. If you just took someone's code that they posted online, you never really looked at it, then you might have a harder time with that question. But it's not a hard question. So that's something you will see here that you don't see. But again, don't just look at the finals because we didn't have midterms, right? So our final will, be more distributed over the semester as opposed to an old final that may or may not be distributed over the semester, may just emphasize the last third of the course.
I have a question about the coding. So
Yeah.
on the final, I assume there will be coding questions. Like, how
No.
would that be
So
graded? Like,
there's some kind of coding, but I'm not taking off points if you don't put a colon at the end of the definition or an if statement. So
Okay.
I'm not playing the role of the compiler or the interpreter. So it's more like pseudocode, but I hate the word pseudocode. Or I don't mind the word pseudocode, but I hate using it with students because students then think, they say like, solve the problem, and that's your pseudocode. So pseudocode should mean it looks sort of like Java, it looks sort of like Python, it looks sort of like C++, right? It means that if someone took the time after the exam was over to turn this into a working program, they would be able to say, okay, yeah, I just need to, fix up the syntax. But when your pseudocode becomes so vague that, a programmer would have no idea how to do what you're suggesting, that's not really pseudocode anymore. That's just, vague ideas. So it's got to sort of look like code, but I'm not taking off, a single point for, non-working syntax, but it's got to be clear what you're trying to do. Okay, did that answer your question?
yeah.
Yeah. Okay.
Can I give like an example? Like, so like I make a function, but like I don't know how to like display it without having to like maybe look it up, but like I explain the function like I'm trying to make.
So
Like say if I want to make like a switch function, like I would like, I know I need to make a switch function, but I can't necessarily remember it.
right, so you could use if statements for that.
Okay.
All right. So use syntax. Again, it doesn't have to be valid Python or Java, but it should look like, you know who does good pseudocode? Wikipedia does good pseudocode. Okay, so I don't know if they're trying to approximate any particular language, but it's very clear what they're doing when they write pseudocode, even though it's not Python, it's not Java, it's not C++. I mean, sometimes they will put real code there, but they generally tend to use pseudocode in their articles about different problems, and they do a nice job with it. But it's just very clear what they're trying to do. Okay. All right, so we're going to stop here. I anticipate that we will have, time at the end of, some of the forthcoming lectures to review a problem here and problem there. So by all means, go over old exams, find things that you want me to clarify, and we should have time. So, be prepared for it. So then we have 20 minutes left at the end of a lecture. You can say, oh, I'd like to discuss full 2008 exam 2 question, whatever, right? And we can go over that. Okay. All right, everybody. So have a nice day. I will see you tomorrow. Any topics in specific we should pay attention to? So dynamic programming is an important topic that will probably show up. There's a recurrence coming, and recurrence with a master theorem. So that's a topic you should pay attention to. I promised you one question relating to empirical performance. So how you would set that up. So that's a topic you should pay attention to. I like parallel computation. So, giving you something you've seen before, asking you to analyze, let's say, the serial version and to come up with some ideas from parallel. Again, the syntax, the Python syntax for that with the multiprocessing and the applied, I don't care about that. Well, about like what we did in the first part of today's lecture. I'm not emphasizing, let's say, memorization. It's more, what have you, the bigger picture. The bigger picture. Just let's say in terms of sorting for a second. So you should be able to code some kind of sort. Yeah, so even if you don't remember the details for 10 sorts, but if I said, write an n log an n log n sort or an n squared sort, you can do one of them. What was the topic after empirical performance? So again, I said dynamic programming. I said a recurrence equation, like what we did today, but not as complicated numbers. Testing empirical performance. Then there are like course-wide topics. So sorting, but also the role of sorting, searching and sorting in other contexts, right? So understanding how those contexts affect other things. Also the role of data structures. So there were a few cases where the choice of data structure made a difference, okay? So understanding how data structures are important in terms of algorithms. Yes, a parallel computation, right? So that's a question that will probably show up. Again, not the syntax, the Python syntax about the apply pool and the CPU count, but the first part. Here's an algorithm, that was a serial, something maybe we've seen before in the course, and then how do you parallelize it, understanding what's easy to parallelize, how not, those kinds of things. All right. Okay, take care, everybody. Bye-bye.